Hello, in this video we are going to look at the variation of parameters method. The variation of parameters method is for going through and finding specific solutions to non-homogeneous second-order differential equations. The method is inspired by the following example. So let's just go through an example and see if we can generate the method. So suppose we're asked to go through and find a specific solution y double prime plus 4y equals 3 cosecant t. So your first thought might be, wait, we've already got a method for going through and finding specific solutions to second-order differential equations. Why wouldn't we just use the undetermined coefficients method? So that we covered that in the last video. Well, the problem with the undetermined coefficients method is that it only works on functions whose derivative look at least similar to the original function, right? So it works on exponential functions because the derivative of exponential function is an exponential function. It works on sines and cosines because the derivatives of sines and cosines gives you more sines and cosines. It works on polynomials because the derivative of polynomials gives you more polynomials. So we don't have any of those cases here, right? So the derivative of things that end up producing cosecant t don't look like cosecant t. And so that's where the method really breaks down. And so we need an alternative method, for when we encounter those circumstances. So what else could we do? How could we go through and solve this? Well, if you think about it long enough, something that might occur to you would be to say, I have no idea what to guess here, so maybe I'll go through and try solving the homogeneous problem, and then maybe that will give me some inspiration. So if you go through and solve the corresponding homogeneous, what happens? All right, so we'd have y double prime plus 4y equals 0. This is r squared plus 4 equals 0. R equals plus or minus 2. And we could form that into y equals c1 cosine of 2t plus c2 sine of 2t. Okay, so we end up getting to here, and then the question is what to do next. All right, so we know that this solves the homogeneous. We are looking for a solution to the non-homogeneous. We want a solution to this. And so if you stare at this long enough and think back to the previous techniques that we cover, an idea might occur to you, and that would be, what if I did variations of the homogeneous? Maybe variations of the homogeneous would end up working on the non-homogeneous, right? And what do I mean by that? So here we've got constant multiples of cosine and sine, and those solve the homogeneous. Maybe there's a variation of those. Maybe there's something instead of constant multiples that would solve the non-homogeneous. And so what you could do at this point is say, you know what? I'm just going to take a wild guess. Maybe something of the form y equals u1 cosine 2t plus u2 sine 2t. Maybe if I did that where I had functions here instead of constants, then maybe that could end up working on, something of that form could end up working on the non-homogeneous. Okay, and so that's a little bit similar to what we did in the repeated roots section, where the idea came up. It was like, oh, well, we need something whose derivative would be e to the at other than e to the at, and we're like, hey, well, maybe we could put a function in front of e to the at, like t e to the at, and that's where that came from. And so it's really the same idea, just coming back a second time in a slightly different context. Okay, so we go through and we guess this, and then we hope that we could find something that we could put here and here that will solve the non-homogeneous instead of solving the homogeneous, like the one with constant multiples. Okay, once you make your guess, from there, it's just a matter of going through and doing what we've done in previous sections, and that is find what the derivatives would be and then plug them in. All right, so let's go to the next page. We have y equals u1 cosine 2t plus u2 sine 2t. And we could go through and find y prime. That would be u1 negative 2 sine 2t plus u1 prime cosine 2t plus u2 2 cosine 2t plus u2 prime sine 2t. And then we can go through and group these. So we're going to take the non-derivatives first. So we'll have negative 2 u1 sine 2t plus 2 u2 cosine 2t. And then after that, we'll have u1 prime cosine 2t plus u2 prime sine 2t. Now at this point, we're going to do something strange. We're going to go through and take this second part of this equation for y prime, and we're going to say that has to be 0. We're going to add a requirement. We're going to require that u1 prime cosine 2t plus u2 prime sine 2t has to equal 0. Why do this? Well, it's not obvious right now why you would do this. It doesn't really make any sense. It just kind of comes out of nowhere right here in the middle of the problem. However, if you did not do this and you just went ahead and kept going, calculating derivatives, plugging them in, then the issue that you're going to run into is that when you get to the end where you've got y prime, and y double prime, and then you take them and plug them back into the differential equation, you won't be able to go through and solve for what u1 and u2 are. So in adding this requirement, it's going to enable us to go through and solve for u1 and u2. So it does come out of nowhere. It does seem like a really weird thing to do. But if you don't do it, this is kind of where the derivation kind of involves, someone at some point went through and tried this. They got to the end and they said, this doesn't work. And then they added this requirement and then suddenly it did. And so we're just kind of cheating, and we're using the fact that we're going to end up getting there to kind of see into the future and say, you know what, we're just going to add this requirement now rather than go through, get to the end, not be able to solve, come back, add the requirement. So we're just going to do it right in the middle. Hopefully that makes sense. Okay, so once you've done that, that gets rid of these, right? So now we're going to go through and calculate the derivative, and we're going to end up calculating the derivative on just these two guys here. So we're going to have negative 2 u1 times cosine 2t plus negative 2 u1 prime sine 2t, and then 2 u2 negative sine, oops, I forgot the 2. And we're going to have the same thing here. So negative 2 sine 2t, and then plus 2 u2 prime times cosine 2t. And then we can go through and clean this up. We're going to sort it just like we did before. So we'll have negative 4 u1 cosine 2t, and then negative 4 u2 sine 2t, then negative 2 u1 prime sine 2t, and then positive 2 u2 prime cosine 2t. All right, so now we have u double prime, u prime, sorry, we have y double prime, y prime, and y. We can go and plug all of those into our equation, right? So our equation is y double prime plus 4y. So that's going to equal this whole thing. So we're going to have minus 4 u1 cosine 2t minus 4 u2 sine 2t minus 2 u1 prime sine 2t plus 2 u2 prime cosine 2t. All right, and then we have plus 4 times our original, so plus 4 u1 cosine 2t plus 4 u2 sine 2t. All right, and so we've got minus 4 u1 cosine plus 4 u1 cosine. Those cancel. We have minus 4 u2 sine 2t plus 4 u2 sine 2t. Those cancel. And so we end up getting just this. Oh, and then I forgot it has to equal 3 cosecant t, right? And so the result that you get from that is that negative 2 u1 prime sine 2t plus 2 u2 prime cosine 2t has to equal 3 cosecant t. And here's where that foreknowledge to go through and put this requirement, use this requirement earlier in the problem. Look at this. Look at this equation that we ended up with. You know, as a consequence of making that requirement, we ended up with an equation that has u1 prime and u2 prime in it. Those are the unknowns. Everything else is known. Look back at the requirement that we had. u1 prime, u2 prime. So now we have two equations with two unknowns, which we can then go through and solve for. If you don't add this requirement, then you'll get to the end and you'll have a much more complicated differential equation than this, right, with u1 and u2 primes. You'll have u1 double primes and u2 double primes. It'll just be way more complicated, and you only have one equation. We need two equations. So adding this requirement is this brilliant thing that enables us to go through and create this system that we can solve to get u1 and u2. So let's do that on the next page. Let's go through and solve that system. Okay, so hopefully copied that right. So we got u1 prime cosine, u2 prime sine, u1 prime cosine, u2 prime sine. Okay, looks good. All right, so the next step to go through and solve this system is we're going to use the substitution technique for solving linear systems. So we're going to solve for one of these variables and then plug into the other equation. Let's go through and take this equation because it's simpler, and we're going to go through and solve for u2 prime. All right, so what happens, we're going to have u2 prime sine 2t equals negative u1 prime cosine 2t. Then we're going to get u2 prime equals negative u1 prime cosine 2t divided by sine 2t. All right. And then once we've done that, we're going to then take that and we're going to plug it into the other equation so that we can solve for u1 prime. So the end result is that we'll have an equation that just has u1 prime in it. So let's do that next. So we're going to take this and we're going to combine it with this. These two go together. And we're going to get negative 2 u1 prime sine 2t plus 2 times, u2 prime. So where the u2 prime is, we're going to substitute. Okay, and then we still have this sine 2t. Oop, hold on. We still have this cosine 2t, I should say. And then equals 3 cosecant of t. All right, so the next thing we can do is we can go through and do some simplifying. So negative 2 u1 prime sine 2t. And then here we're going to end up with minus, we're going to have 2 cosine squared 2t over sine 2t equals 3 cosecant of t. So here I just took cosine times cosine, moved the negative 2. Oh, and then somehow I lost the u1 prime. Let's put that back in. Okay. And then at this point, we can go through and we can factor out the negative 2 u1 prime. So I'm pulling out the negative 2 u1 prime there and the negative 2 u1 prime here. We get sine 2t plus 2 cosine squared, not 2. Sheesh. Cosine 2t squared over sine 2t equals 3 cosecant t. And then we can get common denominators here. This is going to be negative 2 u1 prime. And if we do that, we'll have sine squared 2t over sine t 2t plus cosine squared over sine equals 3 cosecant of t. And so what happens here? So that's going to simplify. Sine squared plus cosine squared is 1. So we get 1 over sine 2t equals 3 cosecant of t. Right? And if we multiply on both sides, we're going to get u1 prime. Right? That's going to equal negative 3/2. Okay, because we're moving the 2 over. And then we're going to have sine 2t times cosecant t. Okay. And then the last thing we can do is we can go through and use the identity. So we're going to have u1 prime equals negative 3/2. The identity for sine 2t is going to be 2 sine t cosine t times cosecant t. And then finally, still working our way through this, sine times cosecant. So cosecant's 1 over sine. So those are going to cancel. The 2's are going to cancel, right? And we're left with negative 3 cosine of t. All right, so that's what we end up getting for u1 prime. All right, and now that we have u1 prime, so this is just a very complicated linear equation. If you use the substitution method to solve a linear equation, you solve for a variable, then take that variable, substitute into the other equation so that you have a single variable, solve for that variable, and then go back and take that solution and plug back into your original solution to get the original variable that you isolated. So let's do that on the next page. So we have one of the two, but we still need to get u2 prime. And to do that, we're going to take u1 prime and plug it into this. So we have u2 prime equals negative u1 prime times cosine over sine. We have cosine 2t over sine 2t. All right, and so now we're going to solve for that. We're going to plug in our u1 prime. So our u1 prime is negative 3 cosine t times cosine 2t over sine 2t. Okay, so to go through and simplify this, we're going to have, this is 3 cosine t, and then we're going to convert our cosine 2t and our sine 2t into, we're going to use trig identities to convert those. All right, so we're going to take the cosine 2t and we're going to write it as 1 minus 2 sine squared t. And then we're going to take the sine 2t and write it as 2 sine t cosine t. And then if you do that, look at that. We've got the cosines. They go away. Let's just pull the 3/2 here off to the side. So we're going to have 3/2. And then we'll have 1 minus 2. Oh, hold on. Okay, so if you take 1 over sine, so that's going to give us another cosecant t. And then 2 sine squared over sine, we're going to have minus 2 sine t. And then finally, we can distribute that 3/2. We'll have 3/2 cosecant t minus 3 sine t. Okay, so that's u2 prime. Let's just kind of take a moment and pause and see where we're at. All right, so we have u1 prime equals -3 cosine t, and we have u2 prime equals 3/2 cosecant of t minus 3 sine t. Right, so what we're interested in is not u1 prime and u2 prime. If we go all the way back, we're interested in u1 and u2. So how could we get u1 and u2 if we have u1 prime and u2 prime? We could integrate, right? So if you find the antiderivative of both sides here, you're going to get u1 equals -3 sine t plus c. And then if you integrate here, you're going to get u2 equals 3/2. The antiderivative of cosecant of t is natural log cosecant of t minus cotangent of t. Now, you might need to look that one up. All right, and then the antiderivative of -3 sine t is going to be plus 3 cosine t. And we'll use different c's here, so plus c2. So when we integrate, we're going to have these c's that are in here. All right, now what happens if we go through and take those two solutions, go back to the beginning, and plug them into our guess, right? Into our guess here, what happens? Let's go to the next page and do that. So we're going to have y equals, and then we're going to have u1. What was u1 again? It was -3 sine t plus c1. Times, what did we get? What was the rest? Cosine 2t. And then plus u2. u2 was this long thing. 3/2 natural log cosecant t minus cotangent t plus 3 cosine t plus c2. Right? And we have that times sine 2t. Yeah, sorry for that little jog there. There's a, when you're recording in Zoom, there's a permanent button that's right where the sine 2t should go. And so it's I had to write above that button. All right, if you go through and multiply this out, what happens? So we're going to get -3 sine t cosine 2t plus c1 cosine 2t plus 3/2 natural log cosecant t minus cotangent t sine 2t plus 3 cosine t sine 2t plus c2 sine 2t. Okay, so what we can do here is we can go through and use some trig identities to try and clean this up. You get negative 3 sine t, and then cosine 2t we can replace with 2 cosine squared t minus 1, then plus the c1 cosine 2t, plus the 3/2 natural log cosecant t minus cotangent t sine 2t. We're leaving that one alone. And then we need some more space here. So plus 3 cosine t times sine is 2 sine t cosine t plus c2 sine 2t. And then finally, almost done. If you multiply this out, we're going to have minus 6 sine t cosine squared t plus 3 sine t plus c1 cosine 2t plus 3/2 natural log cosecant t minus cotangent t sine 2t plus 6 sine t cosine squared plus c2 sine 2t. Whew. All right, and then this cancels with that, all of that for just for that little cancellation there. All right, and then last we're going to go through and do some reordering here. So we've got a c1 cos t, a c2 sine t. Let's put those first. Then after that, let's put the rest. So we're going to have 3 sine t. That's from right here. And then this monstrosity, 3/2 natural log cosecant t minus cotangent t sine 2t. All right, so that's what we ended up with when we took our guess at what will solve the second order differential equation, the non-homogeneous second order differential equation, and plugged in the u1 and u2 that we found. So in doing that, since we took this and plugged it into this to find it, the thing that we just found is something that we could plug into the non-homogeneous that will make it true, right? So this is going to work for the non-homogeneous. This big thing that we just found, this is going to be a solution, it's going to be solution to the non-homogeneous. Now look at that. Look at that. That's a solution to the non-homogeneous. What does it look like? It looks like the result that we got in the last section, which said that if you went through and solved a non-homogeneous differential equation, what you could do is you could combine it by taking the solution to the homogeneous and then add a specific solution to it. So this is the solution to the homogeneous. And then that means that, what does that mean about this? That means that this whole thing, this is the specific solution. So let me explain that again, right? So we went through, we found this y, we found it by taking our earlier guess and plugging it into the non-homogeneous differential equation. That means that this solves the non-homogeneous differential equation. And then if you recall from the previous video, we had a theorem that said that solutions to non-homogeneous differential equations look like this, where you have the solution to the homogeneous first, and then you add to it a specific solution to the non-homogeneous. By matching up the first part and saying, hey, this part is the solution to the homogeneous, that implies that what's left is going to be the specific solution. Okay, and so that's our technique for going through and finding, that's our variation of parameters technique. That's the technique that you can use to go through and find additional, specific solutions to the non-homogeneous. You can go through and you can guess y equals u1 cosine 2t, u2 sine 2t, then you can differentiate. Then you can assume that parts of it's going to be 0. Then you can differentiate again. Then you can substitute in. Then you can simplify. Then you can create a system of equations. And then you can go through and solve the system of equations. And then once you've solved the system of equations, you can then integrate. And then when you could take the solution of your integration and plug it into your guess, and then you could do a ton of simplifying. And that this right here will be the specific solution. It's a great method. A little bit long. So a good question at this point is there any way to shorten that? That's kind of a lot. And the answer is absolutely, there is. Okay, so that's the next thing that we're going to do next. How do we go through and generalize this method and hopefully shorten it? All right, so to do that, what you're going to do is we're going to go back to the beginning, except instead of having a specific problem, we're going to take this whole thing and we're going to generalize it. We're going to make it generic. All right, so suppose we have a second order differential equation that's non-homogeneous. So here's our general form for a second order differential equation that's non-homogeneous. What we're going to do is we're going to suppose y equals c1y1 plus c2y2 is the general solution to the homogeneous. Right, that's the same thing that we did last time, is we went through and found the general solution to the homogeneous. Now we're going to note here that since this is the general solution to the homogeneous, that means that the Wronskian of y1 and y2 is non-zero. That's going to matter. Okay, once we've done that, so again, we're following in the steps. If you go back and compare the steps that we used to solve that the problem that we had earlier, the specific problem that we had, with a bunch with P's and Q's and G's all plugged into this, we're following the same set of steps. So what we did next is we went through and we guessed that y equals u1 y1 plus u2 y2 would be a solution, could be a solution for some u1 and u2. All right, that we would need to solve for. Once we do our guess, the next thing you can do is we would differentiate it, and so we're going to get u1 prime y1 plus u1 y1 prime u2 prime y2 plus u2 y2 prime. And then this is the point where we reorder this. This is u1 y1 prime plus u2 y2 prime, and then plus u1 prime y1 plus u2 prime y2. And this is the part where it kind of comes out of nowhere, but we're going to say we're going to require u1 prime y1 plus u2 prime y2 to equal 0. The consequence of that is that this whole piece goes away, and then we can go ahead and take the second derivative for y, and that's going to be u1 y1 double prime plus u1 prime y1 prime u2 y2 double prime plus u2 prime y2 prime. Okay, and then once we have all of those things, now we're going to take those and we're going to plug them into so the next thing that we did when we went through and did this the first time, we took that result and we plugged it all back into the original differential equation. So let's do that. All right, so we're going to have this here first. All right, so actually let's do this. All right, so we have y double prime plus py prime plus qy equals g. All right, and then y double prime is this. So it's u1 y1 double prime plus u1 prime y1 prime, and then u2 y2 double prime plus u2 prime y2 prime. Then we have plus p times this thing without the second part. So we have u1 y1 prime, u2 y2 prime, plus q times y, which is our original guess, u1 y1 plus u2 y2. And then all of that has to equal g. All right, so we want to take that and we want to do some simplifying to it. So what we're going to do is we're going to go through and we're going to group up the U1s and the U2s, and nice things are going to happen, right? So we have U1 times Y1 double prime, U1 times PY1 prime, and then U1 times QY1. All right, and then we're also going to have U2 do the same thing. So we have U2 Y2 prime, double prime, plus, and then we're going to have P y2 prime. So that's from right here. And then we'll also have Q y2 from right there. Okay. And then what's left? What did we not end up using? So this was anything that had U1 or U2 we used. So we're going to have U1 prime Y1 prime. All right. That guy is in here. U2 prime Y2 prime. And that should be it, equals G. And then look at this. So what do we know about y1? Well, we know that y1, if you plug, y1 is a solution to the homogeneous. So if you take y1 and you plug it into this, then you're going to get 0, right? That means that y1 double prime plus py1 prime plus qy1 equals 0. Y2 is also a solution to this. That means if you take this and take y2 and plug it in, you get y2 double prime plus py2 prime plus qy2. That's all going to equal 0. All right, so what does that mean? That means that this is 0, this is 0. Both of those terms completely drop out, and we get u1 prime y1 prime plus u2 prime y2 prime equals g. All right, and now here's the part where we go through and create the system of equations. So we just kind of maybe draw a little dividing line here. So we want to take our earlier requirement, u1 prime y1 plus u2 prime y2 equals 0, and combine it with this, u1 prime y1 prime u2 prime y2 prime equals g. Okay, so in order to go through and solve this system of equations, so you remember we solved the system last time, so we're going to have to solve it this time. We start with the easier one that has the 0. So if you recall what we did last time, we solved for u2 prime. So we're going to do u2 prime equals u1 prime times y1 over y2. All right, so I got that by taking this, moving it to the other side. Oh, should be negative. That's the only thing I forgot. That's what happens when you skip steps. You forget little details. Little details that matter. All right, so when this goes to the other side, it's going to become negative u1 prime y1. That's the numerator. And then I divide it by y2 to get u2 prime by itself. Once you've done that, you want to take this, plug it into the other guy. So we're going to have u1 prime y1 prime plus, and then negative u1 prime y1 over y2, right, times, and then we have still this y2 prime equals g. And then at this point, you can go through and factor out the u1 prime. And this is all the same steps. If you go back and compare to the steps we did earlier, it's all the same steps. So we have minus y1 over y2, and then we got another y2 prime over here, equals g. And then if you get common denominators, remember we got common denominators last time, you're going to have y1 prime y2 over y2 minus y1 y2 prime over y2 equals g. So that's going to give us u1 prime. And then here we're going to have y1 prime y2 minus y1 y2 prime over y2 equals g. If you look at this, it should look kind of familiar. All right, now the issue is that it looks kind of like the Wronskian, except the signs are off. So what you can do is you can go ahead and say this is the negative of the Wronskian. And so what we have here, hold on, actually I don't want to do that, equals that. Let's go this way. We can go through and say u1 prime times the negative of the Wronskian of y1, y2 over y2 equals g. And then one more step here, we'll have u1 prime equals y2 g over the Wronskian of y1, y2, and with a negative sign. All right. And now at this point, if we had more room, we would do it on this page. But at this point, you want to take what we got for u1 prime and you want to plug it in to get u2 prime. And again, this is the same thing that we did last time. So we have u2 prime equals u1 prime times y1 over y2. And we have u1 prime. We just finished figuring out that equals negative y2 g over the Wronskian of y1, y2. And then take that, plug it in, and you'll get u2 prime equals negative y2g over the Wronskian of y1, y2 times y1 over y2. The y2's cancel, and you get negative y1 over the Wronskian of y1, y2. Oop, hold on, and there should be a g there as well. Okay. Hold on, let me take, is there something that's missing? And there's a negative sign. This is a negative sign, like that. It's negative u1 prime y1 over y2. That's pesky negative. So you got a negative sign here, and the negatives end up canceling. All right, so now we've got a definition for y1 prime and a definition, or for u1 prime and a definition for u2 prime. The next step that we did was to go through and integrate. So if you integrate, you're going to get u1 equals the integral of negative y2g over the Wronskian of y1, y2 dt. And then we're going to say that after you integrate, you're going to have a constant. And u2 is going to equal the integral y1g over the Wronskian of y1, y2 dt. And then after you integrate, you're going to have a constant. And then take those two results, plug them in to something, somewhere. Plug them in back here at the very beginning into our guess. So we're going to take u1, multiply it by y1, and u2 and multiply it by y2. So we're going to take u1 and we're going to multiply it by y1. And we're going to take u2 and multiply it by y2. All right, if you do that, This is what happens. You're going to get C1 y1 plus y1 integral negative y2. Actually, hold on. Let's just do this. Just save a step. So we're going to get C1 y1, C2 y2 plus y1 integral of negative y2g over the Wronskian of y1 y2 dt plus y2 times the integral y1g over the Wronskian. And that's your result. Okay, now what can we say about that? Well, we can say that has so this piece here, right? So again, this is the same place that we got to at the end of the previous question. And that is that when you get here to the end, what does this y do? This y is the y value that you'd plug into the non-homogeneous that works. You'd plug it into the non. How do we know that it works in the non-homogeneous? It's because you took your guess in y1 and y double prime, you took them and you plugged them into the non-homogeneous. So that means that these things have to work in the non-homogeneous. So this is the solution that we got to the non-homogeneous. And if you break it into two pieces, what do we know about this piece? That piece was the solution to the homogeneous, right? And so what does that imply about this piece? That piece is the specific solution using that previous theorem we got, which said that solutions to non-homogeneous are the homogeneous plus more, and the more is the specific solution. So the more is the specific solution. Okay, and so we're going to go ahead and memorialize that result with a theorem. All right, what we just did is the proof, and so we're just gonna write it up. We're gonna sum up. So if P, Q, and G are continuous, so we integrated at some point P, Q, and G, so those need to be continuous. Are continuous on interval I, and y1 and y2 are a fundamental set of solutions to the homogeneous. Okay, then hold on. Then the specific solution to the non-homogeneous is capital Y equals, what was it? Y1 in negative integral Y2G over the Wronskian of Y1, Y2 dt plus Y2 times the integral of Y1G over the Wronskian of y1, y2 dt. All right, then the specific solution is what we just got. And not only that, the general solution to the non-homogeneous is y equals c1 y1 plus c2 y2 plus capital Y. Okay. Oh, and I should have gotten this. Then the specifically to the correspond. This is the corresponding homogeneous. I forgot to write that. So it's the, you know, if you want to write the equation in here, it's y double prime plus py prime plus qy equals g. Okay, so this is these are the matching, right? The matching homogeneous with the matching non-homogeneous. In case, I mean, that's kind of obvious, but okay. So the proof, it's done. It's written on the previous pages. So if you want to go through and prove this, here's the proof. Just put proof, write all of this stuff. So we did the proof first, and then we memorialized it in a theorem. Okay. So the last thing that we need to do before we conclude the video is to actually try using this theorem. Does it work? Right? That's a good question. Does it work? Let's go through and try it on the earlier problem that we did. Right? So we have y double prime plus 4y equals 3 cosecant of t. Right? So we want to go through and solve this. Okay. So what does the theorem say? The theorem says that we've got P, Q, and G. They're continuous. We need Y1 and Y2 as a fundamental set of solutions to the homogeneous. So you need to start off by going through and saying y double prime plus 4y equals 0. And then r squared plus 4 equals 0. And then r equals plus or minus 2i. And then we get y equals c1 cosine 2t plus c2 sine 2t. All right, and this is the fundamental set of solutions to our homogeneous equation. This is going to be y1, and this is y2. And you can go through, if you want, and calculate the Wronskian, and you get that it's non-zero. So now we've got y1 and y2. Once we have y1 and y2, you're just going to plug it all into this formula, and hopefully out will pop the specific solution. All right, so let's try that. Let's give ourselves some space here. So capital Y, our specific solution is going to be y1, that's cosine 2t, right? Cosine 2t, negative y2g. So we're going to have integral negative sine 2t times g, right? What's g? G is this function on the other side of the equal sign. That's 3 cosecant of t over the Wronskian of y1 and y2, right? So what is the Wronskian of y1 and y2? So we need to calculate that. Let's just do it down here. All right, so the Wronskian of cos 2t and sine 2t equals, so we've got cos 2t, sine 2t, and then the derivatives, we're going to have negative sine, no, negative 2. Hold on, let me rewrite it. Negative 2 sine 2t. And then the derivative of sine 2t is 2 cos 2t. And so what do we get? We're going to get 2 cos squared t plus 2 sine squared t. So that equals sine squared plus cosine squared is 1. So we get 2. All right, so we're going to have 2 down here in the denominator. And then plus, and what was the next part of our formula? We have y2 integral y1g. So we're going to have y2, which is sine 2t, times the integral of y1g cos 2t times 3 cosecant t over 2, right? The Wronskian of y1 and y2, again, is the denominator here. And I kind of ran out of space. There's a dt over there, though, too. All right. So there's our formula. We just need to go through and do those two integrals. And once we're done with those two integrals, we should end up getting the same answer that we got earlier. So you can go ahead and just pull that negative out. So that's negative cosine 2t To simplify this, we're going to change sine 2t into 2 sine t cosine t times 3 cosecant t over 2 dt. And then here we've got sine 2t. And then we're going to replace cosine 2t with 1 minus sine, 2 sine squared t. All right. Times 3 cosecant t all over 2 dt. And just keep simplifying. So we've got sine times cosecant. Those are going to cancel. We've got 2 over 2. Those are going to cancel. And so we have 3 cosine t dt. It's not too bad. And then here we have sine 2t. And so integral. And then we need to do some multiplication here. So we're going to have 3 cosecant t. And then minus cosecant times sine. So cosecant's 1 over sine. So that's going to get rid of one of those signs. So we're going to have minus 6 sine t all over 2 dt. And then let's just do one more set of simplifying. So we have, or actually we can go ahead and do this integral while we're at it. What's the antiderivative of 3 cosines? It's going to be 3 sine t. And then here we've got sine 2t. This, let's split up the 2. So we'll have cosecant t 3 halves cosecant t minus 3 sine t dt. And then we can integrate there as well. So this is going to become, what are we going to have here? Let's just hit fast forward a little bit because we're going to have to do the same simplifying that we did before. Let's go ahead and replace cosine 2t. This is going to be negative, and we're going to end up with 2 cosine squared t minus 1, 3 sine t, not t, it's supposed to be t, not 2. And then here, we're going to end up with, oh, actually, hold on. We do have to hold off on that. Oh, well, that would have been nice. All right, so what are we going to get from this? The antiderivative. So the antiderivative cosecant, that's going to be 3 halves natural log cosecant t minus cotangent t. And then here for the second piece, we're going to have the antiderivative of negative sine. And the antiderivative of sine is going to be negative cosine. And so we're going to get positive 3 cosine t. And almost done. We'll have, if you multiply this out, we're going to have negative 6 sine t. Do you remember this part? We had the same thing happened when we went through and did this before. Negative 6 sine t cosine squared t. And then what do we have? That's going to be plus 3 sine t. We're kind of running out of space. This problem's too big. All right, so we've got 3 halves natural log cosecant. Maybe I should have done it on the next page. Oh, well, too late now. Minus cotangent t times sine 2t. So that's this times that. And then you also have to take this and multiply it by this. And when you do that, we're going to end up using the double angle identity. So I'm just going to skip ahead a little bit. So we have 2 sine t cosine t times 3 cosine t. So when I do this times this, I'm going to go ahead and replace it. And if you do that, look what happens. We have negative sine cosine squared, positive, or negative 6 sine cosine squared, positive 6 sine cosine squared. This cancels with this, and we end up with 3 sine t plus 3 halves natural log cosecant t minus cotangent t times sine 2t. And is that what we got earlier? Let's take a look. That sounded awfully familiar. We got 3 sine t, 3/2 natural log cosecant minus cotangent sine 2t. I believe they are the same. Indeed, they are. All right, and so there's our specific solution. So assuming we were given this problem and we're asked to go through and find the specific solution, that's it. If you were asked to find the general solution, then you'd want to take this and add this to it, add the solution to the homogeneous to it, and that would get you the general solution to the non-homogeneous instead of the specific solution. Okay? If this seems like a lot of work to go through and do, keep in mind how much work it was originally, right? So if you, without the formula, right, we started here, we went through and did this, 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 and this. So it took like 3.5 pages and it got it down to 1 page. So it did improve the length of the problem to go through and use our theorem that we created by going through and generalizing the proof. Okay, so anyway, that's a method for going through and finding the specific solution to a non-homogeneous differential equation. It's called the variation of parameters method. Thank you for watching. That concludes the video. See you next time.